everyone, Dr. Nat here. So we are doing exercises on heat engines and heat pumps and Carnot engine. So if you have not watched the last part to my chapter 15 series, you should watch that first before attempting to do these questions with me. Okay, so let's start. So this is the first question. Wait, let me see, how many do we have? Okay, looks okay. So this is our first one. The work done by the heat engine is equal to 1/3 of the energy it absorbs from a reservoir. So it's saying that work is 1/3 QH. Find its thermal efficiency. Now, the equations for heat engine is, we have the work equation, which is QH minus QC. We also have the efficiency equation, which is work over QH, or QH minus QC over QH. And we also have maximum efficiency when the engine is operating at ideal conditions, and this is TH minus TC over TH. This is the maximum efficiency. This is just the regular efficiency. So now it's asking the thermal efficiency and the fraction of energy absorbed that is expelled to the cold reservoir. So it's asking you, what is QC? What is the fraction? What is QC as a fraction of QH? And this is asking you, what is E? Okay, so let's start. We use blue for this A. So A is E. So E is W over QH. And we have this W is 1/3 QH over QH. So I can cross that out. So my efficiency is basically 1/3, or you can write it 33.33%. Whoops. Okay, kejap. I need to move this a little bit. Percent. Oh, I can't. Okay, just know that it's supposed to be percent. Okay, let me write it somewhere else. Or 33.33%. Okay, moving on to B. What is the fraction of energy absorbed that is expelled to the cold reservoir? It's asking you fraction of energy absorbed. It's not asking you what is the actual value of the energy. It's asking you what is the fraction. What is the fraction of energy absorbed? So we know that the heat engine absorbs QH. So what is a fraction? So what is QC in terms of QH? Okay, so we know that work is 1/3 QH. So work is 1/3 QH, which means that QH minus QC should give me 1/3 QH. But I don't know the values here. But it's okay, we just want to know what is the fraction here. So if I want to solve for QC, I would say, okay, QH minus 1/3 QH will give me the fraction, will give me QC in terms of the fraction of QH, right? So QH minus 1/3 will give me, so 1 minus 1/3 is just 2/3 QH. And this is your answer. Okay, QC in terms of QH. QC is 2/3 of the energy absorbed, but this is the amount that is expelled. So QC is 2/3 QH. So it's not very efficient. Okay, it's expelling a lot of energy. Okay, moving on. Is that the right answer? Yes, of course. Okay, moving on. Determine the coefficient of performance of an ideal heating mode pump. So it's a heating mode pump. So it's a heat pump operating in heating mode. Heat pump in heating mode. Whoops. That pumps heat from a cold reservoir at -20 degrees. So it has a cold reservoir at minus 20 degrees Celsius, but we should convert this to Kelvin. So that is minus 20 plus 273 is 253 Kelvin to a hot reservoir temperature of 40 degrees Celsius. So TH, 40 degrees Celsius, change that to Kelvin, is 313 Kelvin. Okay. So it's asking you what is the coefficient of performance. So remember, if we are talking about a heat pump in the heating mode, we are interested about what is the amount of heat that it can give us, because that is what we want from a heater. So COP for a heater is QH over the work or the electricity bill that I'm paying, which is also equal to QH over QH minus QC. Remember, we are supplying work to a heat pump so that it gives us QH or it expels QC. Let's draw the diagram really quickly just to make sense of things. So a heat pump, this is my pump. I supply the W here, and this guy will take QC from a TC, and it will give me QH to a TH. Okay, and we know that our TC is 313 and our TC is 253 and our TH is 313. So now QH, we can also say this is equal to TH over TH minus TC. So this becomes 253, this becomes 313 over 313 minus 253. This is 313 divided by 60 gives me 5.22. That is the COP for my heat pump. Okay. Does it have any units? No, it doesn't have any units. So let's see the answer. Yay! Got it. Okay. So I forgot to mention that you should modulus stuff. Modulus QH and modulus of QC. Okay, moving on to the next question. Refrigerator has a coefficient of performance of 5. So A. So COP is 5. COP, we know that refrigerator is a heat pump operating in cooling mode, which means that we are interested to know what is the QC that it can expel from the fridge. So the COP will be related to QC instead of QH, and this is the same equation, it is just work. Okay, or you can say QC over work. Sama je. Okay, if the temperature in the kitchen outside the refrigerator, so this is our environment, is 25 degrees Celsius. So that should be our hot reservoir, right? So hot reservoir is 25 degrees Celsius, or in Kelvin it should be 298 Kelvin. Find the lowest temperature that could be obtained inside the refrigerator if it were ideal. So it's asking what is the temperature of the cold reservoir in ideal cases. So in ideal cases, we can use the temperature to solve for our equation. So this becomes TC, TH minus TC. You can do that as well. Okay, so we have COP. So it's 5 equals to TC. We don't know that yet. And TH is 298 minus TC. So I try to solve for TC. That is 298 times 5, 1490 minus 5 TC equals to TC. So this will give me 6 TC, 1490. So TC is 248.33 K. So that is the lowest temperature. If I wanted to convert it to Celsius, minus 273, and that is a minus 24.66 Celsius. So that's pretty cool. Okay, moving on to the next problem. We have a Carnot heat engine. It's a heat engine, so it's supposed to produce work. Between two heat reservoir has an efficiency of 60%. So our E is equal to 0.6. It's asking us find the temperature of the hot reservoir, find TH if the temperature of the cold reservoir is 27 degrees Celsius. So TC is 27. As usual, convert this to Kelvin. So 27 plus 273 is just 300 Kelvin. Okay. And then we know that for a heat engine, the equation for efficiency is this guy. It's how much work am I getting for the input that I'm giving? So it's work done over QH. Or work done is QH minus QC over QH. So using this equation, but because this is a Carnot, I can say that this is also equal to TH minus TC over TH. So we can use this equation. So now our E is equal to 0.6, TH is I don't know, minus 300 over TH I don't know. So solving for that, get TH as we get 0.6 TH minus 300, and then bring 300 over here and 0.6 over here. I will get 0.4 TH 300. So this will give me a TH of 300 divided by 0.4. So I will get 750 K. Okay, so that is the temperature of my hot reservoir in Kelvin. And if it's asking you in Celsius, 750 minus 273 is 477, which is really hot. Okay, moving on to the next one. Let's see the solution. I got 750. Yep, we should get 750. Okay, this is the next exercise. Exercise 15.5. You should be doing this yourself. If you want, you can pause this video, try it, and then we can discuss together. Or if you just want to continue doing it with me, by all means, let's do it. A heat engine performs 200 joules. It's a heat engine, so it is supposed to do work. Work is 200 joules in each cycle and has an efficiency of 30%. So E is equal to 0.3. For each cycle of operation, how much energy is absorbed by heat? So it's asking how much QH is it absorbing? How much energy is expelled by heat? How much QC is it giving out? Okay, remember, if our heat engine, we start with the hot reservoir, which is TH, and we are supplying QH to our heat engine. And not all of this absorbed energy becomes work. Some of it becomes work. Some of it gets expelled. This is why it is not a 100% efficiency, but instead it's only a 0.3. Okay, so this is, so work done is equal to 200 joules. So now let's find out what is our QH and QC. So we know that efficiency is 0.3, and this is equal to QH minus QC over QH. This is also equal to work over QH, and we already know W work is 200, so this is 200 over QH equals to 0.3. So my QH is just 200 divided by 0.3. So that is a 667 joules. Okay, so if I know my QH, I know my work done. This guy is 666.67. I should know what my QC is, which is this guy minus the work done. So WQC is equal to, okay, let's use an equation that you are familiar with. So W is equal to QH minus QC. We know what W is 200. We know that QH is 666.67. Now I can just solve for QC. So QC is, drum roll, so that is 666.67 minus 200. So it's 466.67 joules. Oops. Okay, so that is how you do it. So now this guy is 466.67 joules. So the addition of W with QC should give me QH, because QH is what I absorbed, and then I divide it into work and I divide it into QC. Some becomes useful energy, some becomes expelled energy. Okay, let's see the answer. If I got it right, 66.67 and 466.67. We are correct. That's great. Okay, next one. Whoa, what's this? Let me pause. Okay, so this is our last question for our second law of thermodynamics. So the efficiency of a Carnot engine is 30%, so E is 0.3. The engine absorbs 800 joules of energy per cycle. So we know that this is our QH because it is absorbing. So 800 joules per cycle from a hot reservoir at 500. So the temperature of the hot reservoir is 500 Kelvin. Determine the energy expelled per cycle. We know that when we have a heat engine, we absorb a certain amount of QH. Some of it becomes useful energy, some of it gets expelled, and the expelled energy is called QC. And then we want to know what is the temperature of the cold reservoir, and this is our TC. So let's draw the schematic diagram really quickly. So we have the TH, this is that, and then we have QH, then we have our Carnot engine. And our engine is supposed to do work for us, so we will be getting work, W, and that is QC, and this is TC. Okay, and we know that our QH is 800 joules. Okay, so now we want to know what is QC from this efficiency equation. So efficiency is equal to work done over QH, or QH minus QC over QH, or TH minus TC over TH. So to solve for QC, we can use this equation, E equals to TH minus TC over TH, because we have, we don't have TC. So let's use QH then. Okay. Oh, there's another equation that I forgot to mention. It is QC, so QH over QC is equal to TH over TC. Not sure how useful that is, but let's just keep it there for now. Okay, so A is finding out what QC is. So 0.3 equals to QH is 800, QC is, we don't know, QH is 800, so I can solve for QC. 0.3 times 800, and then 800 minus answer. 0.3 times 800. 800 minus answer is 560. So QC is 560 joules. And then it's asking what is the temperature of the cool reservoir. Now I can use this equation. Yep, I can also use this equation. Let me use the second one just to be, just testing this question out. So QH is QH is what? 800. QC is 560, and TH is 500K. So, and this is, I'm trying to find TC. So TC using this equation. So 500 times 560 divided by 800. That will give me a 350K. Okay, let's see if we got it right. So A, they use QH minus QC over QH. So this is the same answer we got. Here they use this equation instead of QH over QC equals to TH minus TC. So both are correct. You can use either one. Okay? So hope that helps. Take care, stay safe. Bye-bye.